Okay, good morning, afternoon, or evening. Today I will be going over permutations with repetition. Okay, and I'll get into what exactly that means in just a second. So stay tuned. Moving forward. All right, recall normal permutations. With normal permutations, we have n distinct objects to select from. We have n distinct objects to select from. And all right, so that's with normal permutations. With permutations with repetition, and permutations with repetition, not all n objects are distinct. There is some object that appears twice in our collection of objects to choose from. And that I want you to note, another thing that I want you to note, that the formula that we derive today, caution, only applicable only applicable when n equals k, when the number of objects that we have to choose from is equal to the number of objects that we will be choosing. Okay, this whole thing it only works when n is equal to k. Okay, when n is not equal to k, you'll have to take it by case basis. Okay, there is no formula for that one. But when n equals k, this formula that we're about to derive today, it works. All right, so moving forward from here, in permutations with repetition. In permutations with repetition, not all of the objects are distinct from each other, i.e., some of the objects are the same. Some of the objects are considered to be the same character, the same symbol, same object. So let's keep it moving. An example. The word Illinois. This word, it has 1, 2, 3 I's and 2 L's. Okay. In permutations with repetition, this I, and this I is not considered to be distinct. Okay. They are the same. They are considered to be the same exact character. Same here. This L and this L, alike symbols, are considered to be the same. Okay. All right. So, how many, the question becomes, how many ways can I permute? How many ways can I permute the letters of the word Illinois? How many different ways can I permute the letters of the word Illinois? All right. Now, if I try using the normal formula for permutations, if I try calculating this as if alike characters are not if I try calculating the number of permutations as if alike characters are distinct from each other, I would end up with this many permutations. And as you can see, that is incorrect. That's not the correct way to do so. All right, so let's discover what would be the correct way to do so. Moving forward. The reason that is incorrect, okay? The reason that using the normal formula for permutations on n objects is incorrect is because that formula considers these two permutations to be, these two permutations here will be considered distinct from each other. This will be considered different from this. But we're considering alike symbols. That means this I, these 2 I's, these two I's, this L and this L, and this L and this L. We're considering alike symbols, alike characters, to be the same. They are not distinct. And so the regular formula for permutations that you may be used to would not account for this. It would consider these two to be distinct, and therefore it would end up counting. It would end up overcounting. Okay. So how do we? All right. So in permutations with repetition, alike characters are the same. Alike characters are the same. Okay. And by P88, I mean the normal formula for permutations. The number of permutations when we have 8 objects to choose from. When we have 8 objects to choose from and 8 characters to select. This formula will give us too many. It would overfit. It would overfit. Okay. Just another reiteration of what I already said, written down here. Just another quick reiteration. All right, moving forward. How do we account for this overcounting that the normal permutations does? The formula for the normal formula for permutations does. Okay. To do that, we consider 2 scenarios. Okay. We consider 2 scenarios. What are those 2 scenarios? Here you go. Scenario 1. Each letter is distinct, i.e. Here, I'll finish laying everything out before I give the explanation. Okay. So in scenario 1, focus your attention. Here I usually yellow. Focus your attention up here at scenario 1. In scenario 1, each letter is distinct. That means we consider red I to be different from purple I, and red L to be different from purple L, and green L to be different from the other 2 L's. Okay. Now in this scenario, we are counting using the normal formula for permutations that we are used to in this scenario, in scenario 1. So PD is equal to P N N. Okay. In scenario 1. Now keep that in mind. All right.
Hello.
Siri's listening. So that's scenario 1. Scenario 2. In scenario 2. So focus in here. In scenario 2, alike letters are not distinct. Alike letters are not distinct. And so that means that this red L is the same as this purple L. And we denote scenario 2 as such, as that. All right. And the whole goal of this video is to get the formula for this. The whole goal of this video is to get the formula for how we calculate the number of permutations, which is PND. That's how we denoting it. How we calculate the number of permutations with repetition. Okay. All right. So perm. All right. Perm. With repetition. Okay. All right. So PND is equal to the number of permutations with repetition. Okay. All right. So let us keep moving forward. So here I have one specific. I have a specific. Now I don't know how many permutations with repetition there are. with respect to repeated characters. I don't know how many permutations there is with respect to repeated characters. But what I do know, let's see what I do know so far. Here I have one. There could be a million of them. Who knows? Here I have just one of the permutations with respect to repeated characters. This permutation, I'm considering alike characters to be the same. I'm considering them to be not distinct. Okay. I don't know how many there is, but I'm going to just work with this one case. And I'm going to see how many, when I consider alike characters to be distinct, how many, the strategy here is I want to see how many does this one not distinct. Okay. So this one permutation in which characters are not distinct, I want to see how many permutations this one produces if we suddenly consider just the eyes to be distinct. Okay. If we suddenly consider the eyes to be distinct from each other, keeping the L's, these are not distinct. But if we suddenly consider each eye to be distinct from each other, how many different permutations would that produce? Okay. How many different permutations would that produce? Let's see. All right. So PDI. All right. And that is, by that, I mean distinct permutations with respect to I. I'm now considering eyes to be distinct. Only eyes. Okay. And I want to see how many this one example in which alike characters, all alike characters are considered to be the same. I want to see how many permutations how many permutations are produced when I consider the eyes to be distinct. How many permutations of this do I produce when I consider the eyes to be distinct? Okay. How many, not permutations of this whole thing, but how many permutations, where I keep this here, and I keep all of these in their same place. All of these stay in their same place, but we just move these around. How many different ways can we do that? All right. So that's one. That's another. That's another. That's another. And that is another. So how many did we get? We got 3 factorial, which is equal to 6. We got 3 factorial, which is equal to 6. So if we go from considering alike letters to being the same, to considering one of the symbols to being different, if we go from considering alike letters to being the same to distinguishing between one of the symbols, for each one of these, we get 3 factorial of these. Okay. For each one of these, we get 3 factorial of these. All right. Now let's do this all over again, but let's do it with respect to L. Okay. Let's do this with respect to L. We take the same example, the same permutation in which alike letters are considered to be the same, and we see how many permutations are produced when we consider L's, when we distinguish between L's. Okay. Let's continue. Let's see how many we get. There are 2 L's there, and we get 2 factorial, which is equal to 2. Well, we get 2 factorial. We get 2 factorial different permutations when we suddenly distinguish between L's. So this one permutation, when we don't, in which we are not distinguishing between alike letters, produces 2 permutations, 2 factorials, when we begin to distinguish between distinguish between L's. Okay. All right. Now, what if I said, all right, let's suddenly distinguish between both I's and L's. Okay. So now we take this one example, this one permutation in which alike letters are not distinguished, and we figure out how many permutations in which I's and L's are distinguished are produced. How many does it produce? All right. So let's see. If we were to do it, I'm not going to write all of them out, but if we were to do it, if we were to write down all of the different permutations produced by this single permutation in which alike letters are not distinguished, if we were to suddenly start distinguishing between I's and L's, we would get, from this one example in which alike letters are not distinguished, we would get 3 factorial times 2 factorial, which is equal to 12. We would get 12 permutations in which alike letters are distinguished between. Okay. So for every, let's try to establish a relationship between this here and between this. And between PD. In between, here we go. All right. So now we're trying to establish a relationship between this and this. Now remember, this is the number. This is the total number. That right there is the total number of permutations in which alike letters are not distinguished between each other. And we want to find out how many of these do we get. And this is the total number of permutations in which alike letters are distinguished between. Okay. We want to find out how many do we get. All right. So let's move on. So in this case, all right, so for each one of these, now these are the permutations in which alike letters are not distinguishable. For each one of these, we produce 3 factorial times 2 factorial of these permutations. This here is the permutations in which alike letters are distinguished. Okay. For each one of these, we produce 3 factorial times 2 factorial of these. Okay. Now, that's why this here is equal to 3 factorial times 2 factorial times this. And if we do a little bit of algebra, we would get that. Okay. Just by solving for just by dividing this and this. Dividing both sides by 3 factorial times 2 factorial, we get to this down here. Okay. Now, this is a specific case. In this case, we had 3 I's. So number of I's was equal to 3, and the number of L's was equal to 2. That was this specific case. But we're trying to come up with a formula. That's the point of this whole video. We're trying to come up with a formula for this in general, a general formula. We don't want this specific case. So we want to know, what is the case in general? So moving forward, let's figure out what is it. Well, what did I do? What exactly did I do? What did I do? Oh wait. Let's think about it. I ended up taking okay, here. Instead, what if I had 14 I's and 17 L's and 2 S's? I would divide by 14 factorial. All right, so instead, what if my number of I's was equal to 14, and my number of L's was equal to 7, and then if I had I don't know, 10 S's, whatever. Then I would have divided by, instead of dividing by 3 factorial times 2 factorial, I would have divided by 14 factorial times 7 factorial times, and so on. So the pattern here is what is basically just to divide by each repeated all right, so you take here, I'll write it out formally so that I don't want to confuse you. So let AI equal the number of times symbol I appears, okay? In your objects. If you got n objects, and symbol I, you got n objects here, and symbol I appears AI times, okay? Symbol J appears AJ times. Symbol K appears AK times, okay? Let AI be the number of times symbol I appears in your list of objects to choose from. All right. Now, if that's the case, then P N D, the number of permutations in which alike objects are not distinguished, PND is equal to PD, the number of permutations in which alike objects are distinguished, divided by A1 factorial times A2 factorial times A3 factorial, all the way on to AM factorial. All right, where M is the number of distinct symbols, okay?